Okay, so this is for chapter 11. We're going to learn how to explain these properties, the differences in these properties between different molecules, using the idea of different forces between the molecules. So intermolecular forces between molecules. The dispersion forces, dipole-dipole, hydrogen bonding. Dimers is a new one in year 12. And then these three things affect the strength of the intermolecular forces. So how big the chain is, how big the molecule or the atom is, and also how big the non-polar chain is, the number of polar groups or the type of group that you've got, and whether it's a straight chain or a branched chain. So those three things affect the strength of the intermolecular forces. And using those ideas, we're going to explain the differences in those properties. So the first one's boiling points that we're going to look at, and then solubility. So the three intermolecular forces, dispersion. We looked at dispersion last year. It's the instantaneous, when the electrons are moving randomly, they might be momentarily on one side of the atom or molecule, and that makes that slightly negative and the other side slightly positive, and then they'll move back again. So the larger the atom or molecule, the more chance that you have that the electrons will be on one side or the other, so the greater the dispersion forces. So the greater the molecules, the two different molecules are held together, the stronger the forces between them. So the word between is useful. And therefore the more energy that you need to turn it from a liquid to a gas. The more energy you need means the higher the boiling point. So dispersion forces are forces that occur between all molecules. They're the only ones that non-polar molecules have to hold them together, but they occur between everything. Dipole-dipole occur between polar molecules. So polar molecules have a dipole, they have two poles. And so this is one molecule, this is another molecule, so you get a dipole-dipole bond between them. So it means that the slight positive and slight negative that you get are permanent rather than momentary or instantaneous like these ones. So you have a permanent sort of slightly negative side. And it happens because you've got an electronegative atom attached to something that's not it's electronegative. So the electrons spend more of their time up near this electronegative atom. Hydrogen bonding is an example of dipole-dipole. It's a slightly stronger dipole-dipole bond where you have a hydrogen attached to an oxygen, a nitrogen, or a fluorine. I should have written it NOF, like on the periodic table, like NOF, nitrogen, oxygen, or fluorine. Okay, we're going to add the dimers to this year. So boiling points. So if we look at, these are all hydrocarbons, so all non-polar molecules. The difference in electronegativity between the carbon and the hydrogen is not much, so they basically share their electrons evenly. So you can see the boiling point for methane, it turns from a liquid to a gas at minus 164. So basically from 164, 163, 162, all the way up, it's always a gas. So at 165, negative 165, it would be a liquid. So you can see with the negative values, smaller number is actually warmer. And then you get into the positive values. So as you're getting larger and larger molecules, you're having more and more electrons, which means that the chances of the electrons here, these electrons are flowing all around the bonds, flowing. Occasionally they could end up over here, which would make this end, this hydrogen, a little bit negative, and the hydrogen and the carbon down this end a little bit positive. So if the same thing were happening to another propane molecule next to it, then you would get a bond momentarily at this end of the molecule. And then they'd all flow back and the bond would break. But the same thing could be happening here. and then later on, same thing could be happening here. So the more electrons you have, the more chance that you've got that there will be a slight negative, slight positive at one point, which means that you can get bonds between the molecule, this molecule and another molecule. That's what the bonds for these are called, dispersion forces. They're really weak, but the more electrons you have, the more chance that you have of them occurring, and so the greater the dispersion forces you have between molecules. Okay, so if we look at these ones, these have a polar bond, but the whole entire molecule is non-polar because it's symmetrical, slightly negative on both ends. So it's a symmetrical molecule. This one is slightly negative all the way around, so it's symmetrical as well. So even though they have polar bonds, it's not a polar molecule. Okay, so the only things that are holding like one carbon dioxide with another carbon dioxide would be dispersion forces, and the same with carbon tetrachloride. So this turns from a liquid to a gas at -57, and this is warmer at 72. So they both got dispersion forces between them. So the reason is that there's more electrons, greater mass. Greater mass means more protons and also means more electrons. So we need to be able to write that. So first of all, they're both non-polar molecules. Carbon tetrachloride is a much larger molecule, more atoms, more electrons than carbon dioxide, so it has a much stronger dispersion forces, greater chance of the slight positive, slight negative occurring. So these are permanent. These electronegativity, the electrons spending more of their time up near the chlorine. What we're talking about is an extra boost, to make that even more negative, and then this less negative, more positive, which is kind of a bit confusing. I should have got a picture that didn't have those charges on it. It makes it a bit confusing. Alright, so the differences that they have are the dispersion forces that occur, which holds the molecules together more strongly, requiring a higher temperature to separate the molecules and turn it into a gas. So you need to be able to explain it totally. You can't just end your explanation here. Why does it have a higher boiling point? You can't just say it's larger, and you can't just say it's larger and has stronger dispersion forces. You kind of have to continue it on. It's larger, more dispersion forces, more energy needed to turn it, from a liquid to a gas. Fully explain your answers. Okay, so these are skeletal diagrams. This is showing one carbon here, one carbon here, one carbon there, and all the hydrogens have been not even put on. So that's a propane molecule. 1, 2, 3, 4, that's butane, pentane, hexane. So you can see as you get more and more, the molar mass gets bigger, more electrons, greater dispersion forces, the boiling point temperature gets higher because you need more energy. And so when you compare homologous series, they're all exactly the same, the type of bonding between them. So the type of other bonds, this would have hydrogen bonds between molecules, but they would all have hydrogen bonds between molecules. So the reason they're not all 97 is because this would also have stronger dispersion forces. Okay, so we've got hydrogen bonding and dispersion forces. So the difference between all of these numbers is the increasing dispersion forces. If we compared this one to this one, so this here is not a carbon, that's a carbon. So it's 1, 2, 3. So it's propan 1-ol. So that's propan 1-ol, and that's probably about the same molar mass as a butane, even if we compared it to this one. You can see this is a slightly bigger molecule, probably the molar mass, but the boiling point is lower than this. So the dispersion forces are possibly between these two similar, but this one's also got hydrogen bonding. Carboxylic acids, as well as they have another thing called dimers, which we'll look at later, which makes them have a higher boiling point than alcohols. Ethers, these ones, because the oxygen is in the middle, the electrons are being shared with the carbon. It's not a polar molecule, ether, so they have a really low boiling point. Okay. So we compared before, the last one, we compared carbon dioxide and carbon tetrachloride, both non-polar molecules. Now if we compare a non-polar molecule, the same one, no, bite my tongue, we've only got a chlorine, one chlorine, so this is a polar molecule, and that's a polar molecule. So we've got two polar molecules. So always dispersion forces between all molecules, dipole-dipole, but this particular dipole, when it's a hydrogen attached to an oxygen, nitrogen or fluorine, then it's an extra strong dipole-dipole hydrogen bonding. So this has got hydrogen bonding and that one doesn't, which is why the boiling point of that one's higher. Even though this one would have more dispersion forces because it's a bigger molecule. Okay, the hydrogen bonding in that has a greater effect. Okay, so the effect of the functional groups. The more polar the functional group, so a polar, even more polar molecule, like one that has hydrogen bonding, the stronger the intermolecular bonds. So, like I said before, chloromethane is a larger molecule, higher, greater molecular mass than water, and would have stronger dispersion forces. It's also polar and has dipole-dipole bonds. But water has very strong dipole-dipole bonds, known as hydrogen bonds, which hold the molecules together the most strongly, resulting in the higher boiling point. Okay, so we talked about carboxylic acids, slight negative, slight positive. This oxygen here attracts the electrons here, which get attracted all the way up to here. So the electrons kind of moving in this direction overall, away from this hydrogen. They're moving in this direction so much that that hydrogen can actually come off. That's why it's a carboxylic acid, because it will lose this hydrogen. So the electrons are moving away from that hydrogen, makes it slightly positive. And this is another carboxylic acid. So because they've got the two ends like this, they could form hydrogen bonds twice between them, which means that these two molecules are basically kind of held together as if they're one giant molecule. So they can act as if they've got a really lot of dispersion forces. So carboxylic acids, as we saw in the previous slide, have a really high boiling point for their size. Okay, so functional groups have an effect. The shape has an effect too. So these all have the same number of carbons and hydrogens, and they're non-polar, so just dispersion forces between them. So you can see this has a higher boiling point than this one. So straight chain molecules, when you think about it, if you've got another one of these chains right beside it, you can have dispersion forces all the way along. Whereas if you had another one of these sitting next to it, this is kind of sticking out in the way. It's difficult to make a bond here with this gap. So you just get bonds kind of here. So the clumpier they are, the less you have a chance of making bonds with another molecule. So these are called branch. I shouldn't say clumped. They're branched. So the types of branching that you get affect the boiling point. Branched molecules have lower boiling points, less dispersion forces. Okay, remember this has got a carbon, dimethylamine. It's got two methyl groups on it, so it's got two methyl groups. And it's an ethyl, carbon here and a carbon here. Okay, So the nitrogen is more electronegative, so the electrons spend more of their time up here, which makes it have a dipole. When it's on the end, this nitrogen is attached to a carbon here, and a carbon here. It's not attached to hydrogens. So the hydrogens have to be attached to the nitrogen for you to get hydrogen bonding. So when you have the amine on the end, the dipole-dipole, it makes a hydrogen bond. So the boiling point temperature is higher. We haven't looked at all the strong bonds, metallic, ionic, and covalent. We really haven't. Well, we have covalent all the time. We talk about. But if you lost hydrogen and you make like ammonium, ammonium is actually an ion, and it would be attached to a chlorine ion. Ionic bonds are strong bonds, much stronger than all these intermolecular bonds. So that's why the boiling point for a salt is much stronger. Okay, a summary. Boiling point, so the lowest ones, this is increasing, they should go up. Small hydrocarbons have the lowest boiling point. As they get bigger, the dispersion forces get bigger, so the boiling point gets bigger. If they're straight, they also have a higher boiling point. So you need to kind of look at the combination of these things. If you have a really, really large hydrocarbon, even though the boiling point for a small hydrocarbon is small, the bigger and bigger it gets, and if it's straight, you can actually, a really, really long, straight hydrocarbon will actually have a higher boiling point than what's down here. So this increasing boiling point means if you compared molecules that were all pretty much the same molecular mass. So if you compared them and they're all the same molecular mass, then the dispersion forces wouldn't be increasing. That's why you have to compare them to be the same molecular mass. Okay, so if you've got a carbon attached to an electronegative atom, like halogens or oxygen, then they have dipoles, so slightly positive, slightly negative. For ketones, aldehydes, these esters, all of those have dipole-dipole bonds. And then if you take a step up and you've got your hydrogen attached to oxygen, nitrogen, or we haven't got fluorine here at the moment, then they're hydrogen bonding. So if it's on the end, it has the shape has an effect. So the primary alcohols have the highest boiling point of the different sorts of alcohols. Amines are similar. I think I probably should have put them, I don't think they're higher than alcohols, but anyway, amines. Carboxylic acids are higher because of the dimers, and amides are higher too because they can do the same thing as carboxylic acids. Alright, so have a look at this, pause it, work it out. What do you reckon? Which has the higher boiling point? Okay, this is a bit of a trick. Hopefully you realised it might have been a bit of a trick. We're not comparing them. They're not the same molecular mass. So if they were the same, if it was ethane and ethanol, then clearly the ethanol would have the higher boiling point because it's got the hydrocarbon, hydroxyl group. But this one is really, really big. So it actually has the higher boiling point because the size is so large that the dispersion forces have become even larger than the effect of this one hydroxyl group. So ethanol has hydrogen bonds. The individual hydrogen bond is a stronger bond than dispersion. However, heptane is much larger, and if there's enough dispersion forces, then the total intermolecular bonds are stronger in the heptane than the ethanol. So you have to compare like size molecules. Okay, enough with boiling point. Let's do solubility, water molecules. So solubility is what dissolves in what, basically. So in order for something to dissolve in water, water's a polar molecule, has charges, permanent, slight negative, slight positive charges. So whatever's going to dissolve has to have charges as well, has to be similar to water, like dissolves like. So if liquids, so we could be talking oils, or we could be talking solutions, ethanol. Ethanol is a liquid, ethanol, polar molecule. So if two liquids are mixed together, they're said to be miscible. If they don't, they're immiscible. In order to be miscible in water, you need to be polar or charged. So you need to have positives and negatives. And that effect has to be bigger than the non-polar hydrocarbon chain. Okay, so this, if you've got a hydrocarbon chain, then this is non-polar. And in order for the water molecules to be willing to separate and let something in, they're attracted to each other. They're not going to break that bond and let in a non-polar chain. So they'll only let it in if there's a polar bond and the chain is short. So alcohols, carboxylic acids, amines, amides are soluble because they've got they're polar and they have short hydrocarbon chains. So propan-1-ol is soluble, but butan-1-ol is a little bit soluble, but not much. Although haloalkanes, so chlorine, fluorine, bromine, iodine, attached to a hydrocarbon, can be polar, they're not soluble. So those halogens aren't slightly negative enough to make the water molecule be attracted to them. So even though you classify them as polar, they're not polar enough. So there's degrees of polarity. Non-polar liquids are miscible with each other. So different sorts of oils you can mix together. Longer chain length, I've talked about this already, increases solubility, decreases solubility in water. It increases solubility in non-polar solvents. So this butanol, it's a bit soluble in water, but if you did pentanol or hexa-1-ol or whatever, the bigger and bigger you get, they won't be soluble in water, but they will be soluble in oils. So this is even true for polar molecules. Okay, viscosity, how thick it is, and flashpoint. So viscosity of a liquid is its resistance to flow or pouring. So it's a liquid, so it should pour. But if the molecules are all attached to each other, instead of it falling out, they're sort of sticking to each other and it won't flow. So the stronger intermolecular forces, the less the molecules are willing to move. Flashpoint is the lowest temperature at which a vapor, so you've got liquid, and then some of the liquid molecules will turn into a gas and kind of sit above it and do an equilibrium bit of thing. So they turn from a gas to a liquid back again. So you've got a vapor always sitting above a liquid, all sorts of liquids. So that vapor will ignite, burn, react with oxygen to produce a flame when there's a spark, source of ignition. And I've got some videos which I can show you. Okay.